Hello and welcome. We want to start our lesson, that is pressure, and I would like us to start with just the introduction. So yesterday we were just trying, or I was just trying out whether the connection works or not, and therefore today we will be starting officially. So under this topic we have pressure as our topic, and we define pressure as a force acting normally per unit area. Force acting normally per unit area. And under this, again, mathematically, we talk about it as a pressure being given by force over area. So, the SI unit of force is Newton, and the SI unit of area is meters squared, and therefore the SI unit of pressure is therefore Newton per meter squared. Newton per meter squared. So therefore when you are calculating pressure in solids, we should use this formula. So what about pressure in liquid? So which formula now do we use? So we use the formula pressure is given by H log G. And where do we get this formula from? Somebody might ask that. So allow me to take you through on how we get to derive that formula, and we talk about, or we consider cube or a solid that we put water up to a certain level, we'll call H. So this it has a cross-section area, which is the base area, the one I'm shading, and we give it the name A. So the density of this liquid, we'll call it low, or the general word we use for density, low. So according to pressure in solid is given by force over area, and in our case the force will be derived from weight of the water in this container, and the weight is given by mg, or the mass we multiply by the g, or the gravitational field strength. And therefore for us to get mass, again I'll take you back to density. Density is given by mass over volume, and therefore mass is given by density times volume. So the mass, or the weight therefore, which is our force, will be density times volume times g, since the mass is given by density times volume, and we'll have the weight as rho, v and g. So we already have the force, and therefore to get pressure, we are going to say force over area, and our force, which is the weight, is rho vg, we divide by area. We are talking about cross-section area A. And remember, when we talk about the volume is given by the cross-section area times height. So I'm going to have volume as AH. So if I replace this volume with AH, then I have rho AHG, replacing this as volume divided by A. So dividing this by A, I end up with a rho HG. And that's where the formula for density in solid is born, which we say it is H rho G. We just rearrange this, and this is the formula that we use to calculate the density or the pressure in liquids. It also gives us the factors that affect pressure in liquid, because we talk about factors that affect pressure in liquid, and we say one, we talk of depth, and depth is actually the height, and that informs the decision why when dams are constructed, the depth are made, or not the depth but the walls of the lower part are made so strong, because that is where much of the pressure will be concentrated. So when a diver is swimming, the one swimming in the deep sea, or the one swimming so deep, is likely to have a lot of pressure on him than unlike the one who is swimming near the surface. Then we have the other factor. We talk about the density of the liquid. We can also talk about the gravitational field strength. So when we calculate pressure in liquids, we talk about several things. Or when we calculate pressure, we talk about density, the symbol is the one which is low. So we at times talk about, or we'll talk about maximum pressure. Then we have minimum. So when do we talk about maximum and when do we talk about minimum pressure? So let's take, for instance, we are given a cuboid which is in the shape of a matchbox with the dimensions 2, 4 and 1, and then we are told that its mass is 100 grams. Then we are to determine maximum pressure and minimum pressure. So we start with maximum pressure. So in this case, we are going to go for, so when we talk about maximum pressure, these inform us or give the reasons why a needle is so sharp when it is on your flesh, or when your a nail gets into your flesh, it gets into your body so fast and so swift. The same way we talk about when someone is wearing a high-heeled shoe, they are not likely to walk comfortably, since the sharp-pointed heels have very small area of contact and therefore exert maximum pressure on the floor, hence more damage. So when we talk of maximum pressure, we go for least area. And least area, in which way can we put this cuboid such that it has a least area. It is when the dimensions are small and it is on this side. So we are therefore going to talk about 2 by 1, which is the area, which is 2 centimeter squared, and then we are going to change this into meter squared by dividing by 10,000. We get 0.002 meters squared. 0.002 meters squared, and then we need the weight. Weight is needed. We had mass, so weight will therefore be mg. So mass in kilogram, so 100 grams we divide by 1,000 to make sure that it is in kilogram, and then we multiply by g, and on cancelling out we get this to be 1 Newton, and therefore maximum pressure, max pressure will therefore be equal to the force over area, area small or least, and then we have 1, the force divided by 0.002 meters squared. On feeding that on your calculator, we are going to get 1 divided by 0.002. We are going to get 500 Newton per meter squared. So these will be the maximum pressure exacted by the solid here with its least area. So then when we talk about minimum pressure, minimum pressure or the least pressure, it is when the shape as it is lying on its base, as it lies on its base, and therefore the area we consider, so we are going to consider the maximum area, and that is 4 by 2, which gives us 8. So 8 divided by 10,000 to change that into meters cubed, meter squared, we have 0.0008 meters squared, sorry, and therefore minimum pressure will therefore be force over area. Area are big, and this will be 1 Newton. That was the force. This one, the force or the weight, we divide by 0.0008. So then we have 1 divided by 0.008, and we get 0.125 Newton per meter squared. So if you compare the two, now this is actually minimum pressure as compared to this. This is more and this is least. So that is how we solve a problem on minimum pressure, minimum area, and so on. So if you are joining me, so I'm live on YouTube, I'm also live on Facebook, TikTok, Instagram, and in general all my social media platforms, to make sure that you get me loud and clear. And loud and clear, I mean so you can recommend a friend who is in high school to also be learning with me. So the next thing we talk about pressure in liquid. So a question on pressure in liquid. So that was pressure in solid, and pressure in liquid. We'll talk about a simple question that requires to apply the formula that we've just derived in my previous presentation a few minutes ago. So, and we have some cases whereby we are required to apply that knowledge on density in liquid or pressure in liquid, and one of it is this. So I have a question there. This is a YouTube manometer. So determine the value of H. Determine the value of H. So in this case, we talk of the density. We have the liquid X and liquid Y. So they are balancing because their weights are the same. So therefore, we'll talk about H log G is equals to H log G. And by that I mean H of X, density of X, H of Y, density of Y, but G, remember G is constant for all. Therefore, I can do away with the G, the densities, the gravitational field strength, since they are the same. So comparing the height, I'll say H times the density of H, and the density of H should be given, or we have one of the liquid being water, and therefore the density of liquid X is known because it is water, and we talk of density being 1 gram per centimeter cubed. This should be equal to 20 times the density of that liquid, whose density is also known. The density of that liquid is 1.3, and then we are expected to solve for the height. So, and in that case, so therefore I'm going to solve for H. H will therefore be 20 multiplied by 1.3, we divide by 1, and we get that this is 20 by 1.3. We get this to be 26 centimeters, though it might not look real because it has not been drawn to scale. For that case, it has not been drawn to scale for that matter. Another question that apply the same knowledge, we have given that atmospheric pressure is 760 millimeters of mercury, and the height of the mercury in the tube is 600 millimeters. We are required to determine the pressure of the air trapped on the millimeters of mercury. Remember, we are live. I'm live on YouTube, Facebook, and other social media platforms. So I'm going to talk about pressure, which is atmospheric pressure, ATM, is equals to H log G plus the pressure of the trapped air. And the atmospheric pressure we've been given as 760 millimeters of mercury is equals to the pressure due to the liquid column is actually 600 millimeters of mercury, now plus pressure of the air that is trapped. So to get the pressure of the air trapped, we are going to simply subtract 600 from 700 and we get this is 160 millimeters of mercury. 160 millimeters of mercury, and that will be it, and that will be that. So another area whereby we have issues when handling this area, we talk about the pressure due to the gas column, or which is the U-tube manometer. So a gas column are drawn, and then we have the power or atmospheric pressure, and then one thing we should always note is the part of the manometer on one side closed. Then if it is closed, then how we treat that question should be different than when it is open. Why? We will see why. So in this case, we have the atmospheric pressure being, or the pressure due to the gas supply. The gas is here. So we have the pressure considered differently, unlike when we have it like this. Allow me to draw the other setup that we like using, and I'm finding students getting confused with the time. So when the manometer is opened, and then here we have the PG, the pressure should be P, and then this part is open, and then we have a liquid inafika pale, and then we have this height. So those questions are answered differently. Why? Because this part is open, this part is closed, and therefore we talk about the pressure due to the gas supply in the first case, the PG in this second case. Allow me to start with the second case. So we'll talk of PG, the pressure due to the gas supply given by the atmospheric pressure. So remember, atmospheric pressure is acting at this point, while the PG is acting on this side. So they are acting on different sides. There is atmospheric pressure, and there is the pressure due to the height column, H log G. So it is only under this case we are adding. But if you look at this case, the atmospheric pressure is in opposite side with the, so is actually in the opposite side. So we'll actually talk about atmospheric pressure being equal to the pressure of the gas, PG, the pressure of the gas, and the H, and the pressure due to the height column, the H log G, are the one that are acting on the same end. And that is when we talk of PG being equal to atmospheric pressure minus H log G, minus H log G. So anytime we have a question and this part is closed, we always use the negative sign, or we always subtract the pressure due to the height column from atmospheric pressure. Anytime we have this part being open, we always add. So that is another area that I've seen giving students problems, and that's how we should handle it. So the other part is on I think almost finishing. So the other part is on the principle of transmission of pressure, and we say the principle of transmission of pressure states that when pressure applied at one part in a liquid is transmitted equally to all the other parts of the enclosed liquid, and we also call it the Pascal principle, and this is the one that is applied in the, so we are talking about the Pascal principle. It is the one applied in the hydraulic machine and the hydraulic lift. So in that case, we normally have two limbs, whereby one is narrower than the other one, and then we have one part where force is applied. We have force 1, and then the load is on the other end. The load is there providing force 2, and of course here we have a cross-section area 2 and a cross-section area 1, and then we have a fluid here, and we'll also talk about why water is not used in the hydraulic system, because one thing, water is corrosive, and that makes it not fit. So pressure applied at this point, pressure at point 1, we call it P1, is therefore force 1 over area 1, while pressure applied, and this is the pressure applied at this point, and because pressure, according to the principle of transmission of pressure, pressure applied at one point is transmitted equally to all the other parts of the enclosed liquid. Therefore, it means P1 is equals to P2, or the pressure that is transmitted onto this other part, and therefore means that pressure 2 is given, for this case, will be force 2 over area 2. And since pressure 1 and pressure 2 are equal, it means force 1 over area 1 is equals to force 2 over area 2. And we apply that knowledge to solve problems on that question. And I think I'm done, unless there is any question from those watching from Facebook, YouTube, TikTok, and Instagram. I intend to end my lesson there on pressure. So if you have just joined me for the very first time, my name is Mwangi. I'm a teacher of physics and maths. I began teaching on social media platforms a few days ago. I'm on YouTube, and I'm also sharing the same on Facebook, TikTok, and Instagram. So you can support my work by subscribing to my YouTube channel. That is Mwangi JK, teacher of physics and maths, and then we'll be learning together, or we'll be learning as things move on. So thank you for your time, and you can share to your friends, and all will be well. Thank you. Have a good afternoon.